The next item in our hydraulic system that we're going to focus on right now is the master cylinder. The master cylinder is located up by the firewall of the vehicle, opposite from the driver. So as the driver depresses the brake pedal, it's going to push a mechanical piston, and that is going to move fluid through a series of valves and chambers. Basic example is this. Okay? So there is a sealed chamber in this body right here with seals and pistons and springs, and as the push rod depresses this end of the piston, it's going to move that in towards the nose, towards the front of the body. Now it's only open on one side. It's only open on this side. This is a cast iron example, quite heavy. This is a cutaway model of an aluminum body. This has the reservoir for the brake fluid, and the internal workings are as shown here. So the piston would push from this side, and you have one port here and one port here, and that's going to allow fluid into the system. And it's going to displace from the fluid reservoir, and determining from the angle on this, I'm guessing this sits at an upward angle like that, so our fluid level is nice and even. The purpose of our discussion today is going to be how these function, what they do, where the faults can be, and how to repair and service these. So on the basic scale, this is separated into two reservoirs. Our cap has a rubber layer on it that's compatible with our fluid, and you can see this little piece here that's sticking out, and it can actually protrude outward pretty far. Same with our other chamber. So this seal is allowing the cap to vent, and this is important as fluid is displaced out of the cylinder. We don't want our brake fluid to contact the air. A brake fluid is hygroscopic, meaning it absorbs moisture out of the atmosphere, and it has an affinity for water. The more water we get in our brake fluid, the lower the boiling temp, and the weaker our system is against brake fade due to boiling the brake fluid due to the heat that generates at the wheels from the friction and stopping the vehicle. So one method of doing that is through the use of these seals on the inside of a cap. Here's another version of another cap. Same idea. The fluid doesn't have to come into contact directly with the environment. There is some, I mean, as these are removed and installed, you're introducing atmosphere to the brake fluid, so it's not the end of the world if we expose it to air. We just don't want it to be exposed to the air all the time. And this is another model of master cylinder. So we'll get into more of how these work and what to look for. The main function of the master cylinder is to take the driver's input pressure from the brake pedal, and as that mechanical motion enters and depresses the piston in the back side of this, it's going to push that piston in, and then fluid pressure is going to be moved into the outlets to the brake lines. Inside the reservoir, this may be harder to see, but inside the reservoir we have a couple ports at the bottom. Now let me bring this down so we can see a little better. Try not to blind you too much. So deep inside here, there are two ports on each one. You can't really see that one too well. There's a vent port and a replenishing port. Now the reason why we have two ports, what happens to brake fluid as we generate heat at the brakes by stopping the vehicle and converting that kinetic energy into friction at the brakes, and that friction generates heat? It's going to heat up the fluid. What happens to that fluid as it heats up? Fluid expands. So as the fluid expands, it needs to have somewhere to go, because where's the other end of the circuit for the hydraulic pressure? The other end of the circuit, opposite from this, is your brakes. So if the fluid has nowhere to go as it's heated up from the friction of the brakes operating, if the fluid has no way to relieve that expansion, the only way it's going to relieve that is to move the wheel cylinder pistons or the caliper pistons. So in other words, as the fluid heats up, if it's sealed in there, if it's locked in place, it's going to self-apply the brakes as it heats up. So I have this cast iron master cylinder mounted up in the vise. Now the part where I'm clamping it into the vise is on the mounting flange. This is the heaviest, thickest part, and it's where the master cylinder mounts on a vehicle according to design and specifications. When you're putting one of these in a vise, there is a risk of cracking the housing. The cast iron is brittle. The aluminum, if you're working on one that is cast aluminum, this is really thin and weak. So we never want to clamp around the actual body, but if we're working on one, clamp around the ears that mount it to the firewall of the vehicle, or to the other component that it fastens to. Now we have two ports. Two ports. As we apply the brakes, as our piston travels forward, it's going to move fluid out of both of these ports. Now, why are there two ports? A couple reasons. The system is split for safety, so we don't have a failure on one circuit and it affect all the brakes. And also on some vehicles like this one, the master cylinder is split. The master cylinder is split between these two chambers. Now notice the difference in volume of fluid that these two chambers can hold. And this is the reservoir. We have a small reservoir here and a large reservoir here, separated by the cast iron piece in the middle. Now they are completely independent from each other. They don't mix. And when we apply the brakes, fluid from one reservoir goes to one part of the system, fluid from the other reservoir goes to another part of the system. This system, judging by the shape of this and the size of this compared to the size of this, this is a front-rear split on a vehicle with disc brakes in the front and drum brakes in the rear. How do we tell that? As brake pads wear on disc brakes, the amount that they move, what are they being pushed by? We have caliper pistons squeezing the brakes together around a rotor. Those caliper pistons are quite large. The single pistons are a big hefty size. We could have multiple smaller ones, but in general they move a lot more fluid than a wheel cylinder. Our wheel cylinders, if you remember, they're about this big around on the inside of the bore, and they're about that wide, and they're just moving a little bit back and forth. It only takes a little bit of fluid. Now the main thing is, as the brake pads wear, or the shoe lining wears down, that extra space is displaced by the fluid that's in either of the reservoirs. So drum brakes, using very little fluid to move and operate, and their linings don't involve a lot of movement of the actual shoe itself. The smaller reservoir is going to be for drum brakes, and the larger reservoir is going to be for disc brakes. So this one is a front-rear split, front reservoir up front, rear reservoir is the smaller one, the front reservoir is the larger one for the disc brakes. Now systems can be split diagonal, and that'll typically be found on front wheel drive vehicles where if one side fails, there's an example from the text that majority of the weight on a front wheel drive vehicle is in the front, with the engine and transaxle, all the drivetrain components and the axles up front. That's going to take a lot more weight than the rear of the vehicle that's just trailing behind, and then the chassis and all the other components. So if we had a front rear split on a lightweight or a vehicle that was pretty light in the rear and we lost front brakes, our rear brakes are only doing about 20% of the work of the entire system, especially as we stop the vehicle or slow the vehicle down. That weight transfers to the front, and it's actually reducing the amount of weight that's on the rear wheels. So on a front wheel drive vehicle, typically those systems will be diagonal split. So we have one front brake working and the opposite corner rear brake working. If we have a problem or a leak in the system and one of the circuits is faulty, not allowing the brakes to operate normally. So in that case, if there's such a difference in weight, it's likely going to be a diagonal split. Service information is the best way to tell. On something like this, where we can see that this is physically smaller than this, we know that this is not handling any front brake activity. It's a smaller reservoir. It's for drum brakes compared to the large reservoir that's for disc brakes. Just something to notice. And it's an older style master cylinder, cast iron, heavy. On a quick take-up master cylinder, a quick take-up master cylinder, or a stepped bore master cylinder, is used with a certain type of caliper. The name of that caliper, the term used for it, is low drag caliper. So with the low drag, meaning when the square cut seal deflects and it wants to, as that piston is pushed out, that square cut seal is designed to pull it back in. On a low drag caliper, there's a different profile, either on the seal or in the groove that the seal is resting in inside the caliper housing, which allows more deflection. So with more deflection, when we release the brakes, the pads come farther away so it doesn't touch that rotor surface. Even though you're not applying the brakes normally, the rotor and pad may be touching. Now as they touch, that's going to take energy. That's going to transfer energy from the rotating component, that kinetic energy, into the friction material. So the low drag calipers, coupled with the quick take-up master cylinder, is designed to create more of a retraction of the brake pads to limit the amount of friction being generated while it's just driving around normally without the brakes being applied. The way that's done, in order to move that piston more, is what's called a stepped bore. So a stepped bore, you can see inside of there that the front half, or the front section of the master cylinder bore, is a smaller diameter, and the portion that's out towards the rear, or this section here, is a larger diameter. So let's look at the piston. The piston that goes in the front is this. It's about normal size, and that sits right up front here. This spring bottoms out against the front of the bore on the inside of the master cylinder body. So this is going to move fluid out through this port. So this is our secondary piston. This is our primary piston. Look at the difference in size of the front of this piston and the rear of this piston. Now we're inputting mechanical force into the hydraulic system. So as this piston is in place here, as this piston moves, we have an initial high volume of fluid. We have a larger chamber here, and we have a larger piston face. So that's going to move larger volume of fluid into the system. Now, like I said, these quick take-up master cylinders are always paired with a low drag caliper. So the design of the caliper has to go with the design of the master cylinder. They're engineered to work together. Now, as this moves, we're gonna have an initial low pressure movement of fluid. And that low pressure movement of fluid is gonna transfer down to the caliper and help take up that gap quickly. Quick take up master cylinder. Low drag caliper. Low drag, keep the pads away. Quick take up that distance pretty quick. So that's the reason behind this design. So even on a quick take up master cylinder, we still have our circuits separated from each other with a partition in here. The reason for that is if we do have a leak or loss of fluid in one circuit of the hydraulic system, it's going to allow the fluid to go down only so far in both of them before one of them drains completely, and then we can still maintain level in another chamber, another part of the reservoir. So it's a safety feature, keeping the two halves of the circuit. Now, is it front rear split or is it diagonal split? Service information. Now, master cylinders aren't one of those items that's constantly being overhauled. It's another replacement item most of the time. However, on the older cast iron models, you can rebuild them if you can get a rebuild kit for them. Again, the abrasive hone will only take off a light amount of the surface area that we need to clean up on the inside of the cast iron, but on aluminum, it's going to gouge it too much, it's going to ruin it. So there's no point in even attempting to try to hone aluminum. Just like a wheel cylinder, if it's aluminum, it leaks, it's faulty, it gets replaced. If this were to be serviced, we have a snap ring holding tension here on the back side of it. So let's take this one apart. I'm going to stand up. Might get some fluid coming out of this, but if we press on this, yep, fluid. We can press that piston in, and I'm using a screwdriver, a number 3 screwdriver, Phillips, so there's no sharp edges on it, and it works as a good push rod. When we are pushing the push rod manually, we don't want to push all the way till it stops, because we could damage the seals. So in order to get this to take this apart, we need to use some snap ring pliers. There's some little nubs on the end here that fit inside of see if you can see that a little better there. On our snap ring. So before we squeeze that snap ring, I'm going to depress the piston and take tension off of it. And then expect to make a little bit of a mess sometimes. So have some absorbent towels nearby, or a catch tray or something. So here's our primary piston. Now we need to get the secondary piston out of there. Now the secondary piston can either be tapped out if we were to take this and tap it against something and work its way out, or we can be gentle and lightly pull on that with some pliers. More fluid. And that is our secondary piston. Here's the primary, here's the secondary. They fit together just like that inside. We have a lower spring rate on this piece here and a higher spring rate on this piece right here. So this spring is all that we should be pressing against mechanically. This spring here is to help apply the other piston, and if it doesn't apply directly or if there's a problem with the circuit, this mechanical rod in here will eventually contact and bottom out. So if we lose pressure altogether on one circuit, we can mechanically push and it will still move both of the pistons. Couple other things to note here. This piston has 2 seals on this end, 1 seal on this end. The goal is to move fluid to the brakes. This has piston here, or a piston has a seal here and a seal here, and they are cup seals, just like in a wheel cylinder, similar to a wheel cylinder, same idea though. The cup is facing this way and the cup on this one is facing that way, so as we move fluid it's going to expand outward and help seal against the inside of the bore. So just like the wheel cylinders, we would hone the inside of this so we have a good pattern on our crosshatch pattern, clean it out with brake fluid since that's what's going to be run inside of it, and then reassemble it, and then we'll go through the bleeding process. Since the seals are cupped, if we have fluid behind one of the seals, let's use this one. So if we have fluid on this side of the seal and this is moving backwards, that fluid can actually bypass around this cup seal because the cup seal is going to flare out with fluid being on this side. So when we're trying to apply pressure to the brakes, we're going to apply pressure to the brakes, this cup seal is going to expand and it's going to allow us to provide hydraulic pressure. Now when we release the brakes, this has to move backwards through fluid. Well, that fluid is going to bypass around the seal, allowing it to move back to a neutral position. Take our snap ring here. And that's how that looks. You squeeze them. And then once you fit it into the bore, you release tension and it sits inside of the groove that's around on the inside of this bore. We have our setup here with the adapters tightened in place with the tubes looped up and through, and we have a paper clip here with the tubes passing through the paper clip to keep them in place. And here's a better look at how these are positioned. Now there's some air pockets that are bubbling out of the ports and out of the tubes, and we haven't started moving anything yet. So here's what we're going to do. I'm going to depress the piston here, and then we'll see the movement of the fluid. And we're just going little by little. We're not doing full strokes. We're just doing little bits at a time. And what that's doing is it's purging the air from the master cylinder body, and eventually our air bubbles will diminish, meaning we have all air purged from where the piston travels. Sometimes if you let it sit, it'll bubble a little bit more. There's one. And that's just about done being bench bled. Here's a better view of that. So using leverage with your body, you can use just position your hands right here and use your hips and just lean into it. A lot less fatigue. And then once you're free of all air bubbles, you can then remove your ports. I like to leave all this intact and installed on there until it's on the vehicle. And then once it's on the vehicle, then take these off and then connect the vehicle's brake lines to it to make it to lose as little fluid as possible and to not allow air to introduce into the system. So that's servicing master cylinders and overall how they work. How they're split, some indications on the design of them and what to look for. And again, if you're replacing something, look at your new part first. Make sure that it matches your application. The last thing you want to do is find out when you're at the point of installation after you've gone through all this process, made a mess with the fluid, to find out that you need to send it back in a box. Then you got to clean it and make sure it's not getting the box all nasty with brake fluid. So that's it for master cylinders. See you on the next one.